Hello students, my name is Shashank Shekhar. So today is the last class of solution. So in the previous class we have studied all the four colligative properties which were elevation in boiling point, depression in freezing point, relative lowering of vapor pressure and the osmotic pressure. So we have studied all those four colligative properties. Now today we will just see the last lecture and see a little modification in all those formulas which we have studied so far for different colligative property. So basically we will be seeing today the thing that is abnormal molar mass. So in all the colligative properties that we have calculated, we have seen that we can obtain the molecular mass, and that is also the main objective to calculate or to study this colligative property, that is to calculate the molecular mass. But sometimes we get a molecular mass which is not as per the calculated one. In that case we termed it as abnormal molecular mass. So we will see what is that molecular mass and why does it happen so. Then we will just quantify with the help of a factor that has been introduced by Hoff, which is having an abbreviation that is I. So we'll see what is this I, or it is called as the Hoff factor. So let us start moving. So the first we will see what is the result of this abnormal mass. Second, we'll see what is Hoff factor and what is the effect of introduction of this Hoff factor in the colligative property. Again, we will see this effect in two ways. First is association and the second is dissociation. So let us start our today's lecture. So we have seen from the starting only that the colligative property is the property that depend upon the number of solid particles that we have introduced. So it depends only and only on their number and not on their nature of solid particle. So if in any way we can change this number, or in any way the solid particles are reacting or interacting such that the effective number of particles is reduced or less, then in that case we will see an result which is not accurate to the experimental data. So what are the cases? The first case is association. So there may be the case that two molecule dimerize or three molecule trimerize to give one molecule, or you can say one entity, not molecule, entity. Then in that case the colligative property calculated will be wrong. Why? Because we have taken a greater number of particles, because now three particles are acting as one particle. On the opposite side, if we have the dissociation, suppose one particle is breaking down into two components when we are dissolving it in the solution, right? So in that case we will have a dissociation case and the number of particles will increase, and this will result in a molecular mass, calculation of molecular mass which is greater than the experimental data. So the first one is dissociation. So if you look at the dissociation, the number of particle increases, sorry, it is wrongly written. The number of particle, what happens to number of particle? It increases, because suppose we have say NaCl, right, and we dissolve it in water. So you will consider if NaCl has one particle, then it will be wrong. Why? Because NaCl will dissociate in water and give us Na plus and Cl minus. So now the number of particle is what? 2 rather than 1 which we have assumed earlier. Next, since the colligative property depend upon the number of particle and the number of particle has increased, that's why the observed molar mass will be greater than the calculated molar mass. What will happen? The absorbed molar mass will be greater than the calculated molar mass. In what factor, in what quantity, we will see it later on. Next we have the case of association. So what happens in association? The number of particle increases. Yeah, right? Sorry. Oh, it written. So sorry for this confusion. So here it will be number of particle increases. Here it will be number of particle decreases. Now as we all know that colligative property depend upon the number of particles. Therefore, the absorbed molar mass is smaller than the calculated molar mass. So we'll see it. How it will happen, we'll see it. But for now, assume that in case of association, the absorbed molar mass is smaller, and in case of dissociation, the absorbed molar mass is greater. Observed means what? Means observed means the actual one, and calculated means the molar mass we have calculated using the formula. Now, to quantify it, Van 't Hoff gave something called I and termed it as the Van 't Hoff factor. Now this I can be greater than 0 or less than 0, or it can be fraction, it can be decimal, right? So suppose if we have the association, then it will be, let us keep it for a different thing. Now just assume that this is I. This is called as Van 't Hoff factor. In what case it will be what? We will see it later, right? So what is this I? So it is called as Van 't Hoff factor, and it depends upon the extent of dissociation and association. How? What do you mean by extent here? Because we have seen in case of say weak electrolyte that they dissociate only to a small percentage. Why? Because of the say covalent nature, right? So due to this reason, we see an extent. So the I is something associated with that extent, whether the extent of dissociation we talk about or whether the extent of association we talk about. Now it has different definitions. All of these are true. Yes, all of these are true. So the first one is the I is equals to normal mass molar mass by abnormal molar mass. Normal abnormal mass by abnormal molar mass. Okay. Next one is observed colligative property by calculated colligative property. Observed means the experimental colligative property. Okay. And calculated means the ones we have calculated using our formula. Again, we have our I is equals to number of particle before dissociation and number of particle divided by number of particle after dissociation. Like if we have NaCl, the number of particle before association will be 1 and after dissociation it will be 2. In water, suppose we are dissolving it in water. So it will be 0.5. I will be 0.5. So this is our case. Now if we see the change in colligative property, so I have told you earlier that it is calculated by absorbed. Okay, absorbed by calculated. Now we will see all these formulas modified in a way. How? So initially the formula was like this. If you know the formula from the previous class, I have told you that P01 minus P01 minus P1 by P01 was equals to N2 by N1. So this was our initial formula. Now we have introduced this factor I. We have multiplied by I. Similarly, if we have elevation in boiling point, then we can represent it by the formula as del TB is equals to I kBm. Del TB is equals to I kBm. Where I we have introduced the Van 't Hoff factor. In the similar fashion, we have depression of freezing point. So it will be equals to delta TF is equals to I KFM. So you can see in all the formulas we have this I. Likewise, for osmotic pressure of solution, we have this pi is equals to I N2 RT by V. So these are our new formulas and it is the true formulas, right? So this formula should be considered last, not the previous one with the factor I. So if you are given a case in which you are given association or dissociation, then we will consider these formulas only to be true. Now how do we calculate them? So consider a mole of solute which is dissolved in volume of solvent. And suppose that n simple molecules combine to form an associated molecules. Meaning that we are taking the case of association and we are saying that we are dissolving a particle and n particles of those combine to give one entity. Then n particles of A will combine to give A of n. Okay, where an is a particle and one particle specifically. Now suppose alpha is the degree of association in this. Alpha is the degree of association. Then the number of unassociated particle will be 1 minus alpha. So we have taken initially 1 mole, and suppose n is associating, then the number of particle associating will be 1 minus alpha. Okay, and the number of associated particle that will form will be alpha by n. Yes, it will be alpha by n. Okay, how it is alpha by n? So do not get confused with it. It is just, so if you write this one as, if you divide both sides by n, you will get it as A you will get this thing only, where we have divided by n by both sides. Since we have taken 1 mole, so I have just put the formula accordingly, 1 mole. Now upon this association of alpha particles, 1 minus alpha, we have got alpha by n. So 1 by minus alpha is the number of particles of Na, and alpha by n is the number of associated particles. So what is the total number of particles, right? So it will be 1 minus alpha plus alpha by n. So if I write it more clearly, let me write it. So I said that Na particles means n number of A particle are associating to give a particle that is An, right? Now suppose I am considering it for 1 mole, then 1 mole of A will give this much. Suppose at time t is equals to 0, we have 1 mole and initially this is 0 mole. Now suppose that alpha is the degree of association or the extent to which our association will take place. Then at time t, which is at which equilibrium is attendant, we get it as 1 minus alpha by n. This will be right. Okay. Now the total number of particle will be addition of both these two, which will be equals to 1 minus alpha plus alpha by n. This will be our total number of particle, that will be I. It will be I. Now you will ask how it will be I. Yeah, you will ask how it will be I. So I told you earlier the formula that I is equals to number of particles. Let me write it in a different page. I told you the formula. I is equals to number of particle after dissociation or association by number of particle before association or dissociation. This was our formula, one of the formulas I will say. Now we have calculated total number of particle after association as 1 minus alpha plus alpha by n, and I've told you earlier that we have taken 1 mole. So this will be our I. Now I ask you that write this formula in terms of every colligative property. Then how I will write it? Then it will be delta P1. If I am writing it for the relative lowering of vapor pressure, it will be delta P1 P01 is equals to 1 minus alpha plus alpha by n multiplied by n2 by n1 in case of course n1 greater than n2. This will be a formula, modified formula. Similarly, if I write to for osmotic pressure, it will be 1 minus alpha plus alpha by n into N2 by V RT, or you can write it as this. Similarly, elevation in boiling point can be written as 1 minus alpha plus alpha by N kb m. Again, delta TF can be written as 1 minus alpha plus alpha by N kf m. Now these are our new formulas. After association, where alpha is the degree of association. So if you want an example, we can have this as an example. So if you have seen the hydrogen bonding in case of acetic acid, it looks like this. Okay, so this will be H, O, then C. It will be H, O, like this. So this is our thing. So this is our acetic acid. This is our acetic acid. Now if you have said that alpha is equals to 100%, this with the percentage of association is 100. So what will be alpha? Alpha will be equals to 1, because 100% means 1, right? Then the formula is I is equals to 1 minus alpha plus alpha by N. What is an N here? What is the N here? N will be 2, because dimerization is taking place. 2 solute particles are dimerizing. So the formula will be 1 minus alpha, alpha is 1 here again, plus alpha is 1 here again, divided by 2. So this 1 will get cancelled, and we will get I is equals to 0.5. I will be equals to 0.5. So you can see here that in case of association, since the number of particles has been reduced, therefore we can write that, what we can write, suppose this is I is equals to 0.5. If we put 0.5 in every formula we have calculated earlier, okay, we can write this. And what is this N2? So if you simplify it further, it will be W2 by M2 into M1 by W1. Similarly, here it will be W2 by M2. Again, here it will be N2 by W1, or we can write it as W2 by M2 into 1 by W1. Again, W2 by M2 into 1 by W1. This will be our formula again. Now, if you put this M2 on this side, then you will see that there is a 0.5 factor reduction. Means the molar mass that we have calculated without the introduction of I is 0.5 times smaller, actually half. So we can say that on association, the molecular mass or the molar mass that we calculate will be half. Therefore, we introduce this factor 0.5. So you must try this exercise and let me know what will be the relation between the initial molar mass and the final molar mass for each of these. So if you want, I can do it for one of this. So let me write it on a different page. Suppose I am doing it for this, which will be delta P1 by P01 is equals to 0.5 multiplied by, what was it? It was given mass by molar mass into M1 by W1. Now if I bring this thing here, it will be M2 is equals to 0.5 multiplied by M1 W1 into P01, or you can say it P01 by delta P1. So this will be our new M2 rather than this. So if this I was not here, so we can replace this whole thing by initial M2. Suppose I am saying it as M2 dash. This one is M2 dash after 0.5. So you can see that this M2 dash has been reduced by 0.5. So this should be clear. Now next we have the case of dissociation. What do we have the case? We have the case of dissociation. So let us consider the dissociation of A into N molecules. Now we have taken one molecule of A again, and we are saying that this A is converting into N alpha. Okay, A is converting into N number of P. Then what will happen? 1 minus alpha will give you N alpha. Again, what is the total number of moles at equilibrium? It will be 1 minus alpha plus alpha by N by alpha. 1 minus alpha plus N alpha. How? We will add all these three. 1 minus alpha plus N alpha. Right? Now again, the number of particles after dissociation by number of particles before dissociation. Before dissociation, we have only 1 mole. After dissociation, we have sum of all these three. All these two terms. So we will get it finally as alpha is equals to I minus 1 by N minus 1. So if you want, you can simplify the previous formula also for alpha. Suppose the previous formula was I is equals to 1 minus alpha plus alpha by N. So if you want to calculate alpha, it will become I minus 1 by alpha by N minus alpha, or we can write it as alpha is equals to I minus 1 by 1 minus 1 by N minus 1. So there is only one difference between both of these. So alpha is equals to I minus 1 by 1 by N minus 1. This is for association. And for dissociation, it will be alpha is equals to I minus 1 by N minus 1. So this were the two of this case of abnormal mass. So with this, the chapter is over. Now let us get a quick revision of all this whole chapter. So where we have started from? So we have started from the part that we are dealing with a solution phase. Okay, we are dealing with solution, and we see that solution can be of two types based on the uniformity of solid particles, which was homogeneous and heterogeneous, right? Then we said that in this class we will only study those solutions which are homogeneous in nature. And again, we have put one more filter, which was binary homogeneous solution. So we will specifically study about binary homogeneous solution. What is this means of binary homogeneous solution? Means there are two components. First is the solvent, second is the solute. And if solute is mixed into the solvent, then solute gets uniformly distributed in throughout the solvent. Then there are only two particles. Then we have seen that we can have many cases. First was that each of these can be solvent and each of these can be solute, which give rise to 3 plus 3 plus 3, 9 cases. Okay, which give rises to 3 plus 3 plus 3, 9 cases. First, we have the solid as solvent, and we have dissolved liquid, gas and liquid, gas and solid. First was this. Then we have this liquid where we dissolve liquid, gas and solid. And we have this gas and we again dissolve liquid, gas and solid. So this gave us 9 cases. Means 9 types of solution. Again, we have seen some concentration terms, which was basically you can say mainly for this defining the concentration, because we cannot define it by counting the number of particles. It is literally not imaginable also. So what do? We have defined something called concentration. And for different type of solution, means if you have solid in solid, we will use different concentration term. If you have gas in gas, we will use different concentration term. And if you have solid in liquid, we will use different concentration terms, and likewise. So for that, we have different kind of concentration. The first one was weight by weight percent, means the given weight of solute by total weight of the solution that we have multiplied by 100. The first was this. Then we have volume by volume percentage, in which we said that we have volume of solute divided by total volume into 100. Mean the number or the weight of solute particles that is present in 1 unit mass of this solution. Then we move to this ppm. It is again the same fraction, means the number of solid particles by total number of say solution particles, and multiplied by 10 to the power 6. What it is multiplied? It is multiplied by 10 to the power 6. Why am I multiplying by 10 to the power 6? It is done if in the case we are having a very small, minute number of solid particles. So suppose we have to define the toxicity in presence of water. Suppose we have arsenic dissolved in it. So the toxicity of a small amount is also harmful for my body. So we have to deal with very small numbers. So the percentage will give us 0.000 something, and it will be very difficult to handle. So in that case, what we have done, we have introduced this ppm, that is parts per million, the number of particles that is present in 10 to the power 6 number of solution. That was our case. So it can be either weight of solid particles by total weight of solution into 100, or volume of solid particles by total volume of solution into 100. Means in every 10 to the power 6 part, what is the part of the solute that we have. So this is our ppm. We can have also ppb. So that's a different case. We will take ppm. Then the most important of the 3 came mole fraction, molality. What is this mole fraction? Very simple. It is mainly used for gases. First of all, I'm not telling that we are restricting it, but we often use this mole fraction for gas solution, in which solvent is also gas and solute is also gas. Then we will say that mole fraction is equals to the total number of particles of solute by total number of particles. Again, we have this molarity. What is this molarity for? It is number of moles of solute divided by total volume in which that solute is dissolved. Yeah. So it is number of solute particles, number of moles of solute particles divided by total volume of the solution. Then again, we have this molality, in which we said that it is total number of moles of solute divided by mass of solvent, which is given in kg. So this was specified. Okay, right. It was specified. And we said that molarity is a more better one than molality. Why is it so? Because molarity changes with temperature, and we want to keep a check on temperature. That is why we said that okay, we use molarity more often, because the volume changes with say our temperature. We know that PV is equals to nRT for gas, and also at higher temperature the liquid solution will get a smaller volume due to evaporation. So for that case, we take molarity to keep the temperature at check. Then we arrived at solid into liquid, which was first of our solution, in which we said that as we increase the temperature, the solubility of solids in liquids increases, and as we cool down it, the solubility decreases. What is the live example of it? Take a sugar solution, then keep it in a freezer. You will see that after some time, the crystals of say sugar will start appearing in the solution due to crystallization. And if the opposite case, if we increase the temperature, then the number of solid particles that was initially say dissolving will increase gradually as we increase the temperature, which says that on increasing the temperature, since it is increasing, that means this dissolving of solid into liquid is a endothermic process, and the reverse of it will be the exothermic, means heat will be released, right? So this was our case. That was for solids and liquids. Again, we have seen the effect of pressure on it. So it has negligible effect of pressure because solid is near to non-compressible state of matter. So it is not compressible in nature. So it has the pressure has no effect on solubility of the solids and liquids. Again, we move to the next type of solution, which was that we are dissolving gas in liquid. What we are dissolving? We are dissolving gas in liquid. So it has also two parameters. The first one was was effect of pressure, and it was seen that the solubility of gases increases when we increase in pressure, and it was a direct result of the Henry's law, which says that the partial pressure due to, or the vapor pressure due to the particles is directly proportional to the mole fraction. Then we have introduced a Henry constant, that was Kh, and I said that Kh is specific to the solid particles that we are dissolving. Sorry, solvent particles that we are using for dissolving the next solid particles. Now, as this Kh value increases, the solubility decreases. This was one of our result. Then we have seen the effect of temperature. So we have seen that if we increase the temperature, the solubility decreases, which says that it is reverse of the solid in liquid solution, means it is exothermic in nature, right? The dissolution of, say, gas in liquids is exothermic in nature. So this was our case. So what is this word dissolution? Keep this in mind. It is dissolving of the solid particles in solvent. So we came up with this Henry's law, and with this Henry law was over. Next, we moved to this Raoult's law, and it basically deals with the liquid in liquid solution. So what we told that the vapor pressure of the component 1 is directly proportional to the mole fraction of the particle, particle that is in solution, in which we remove the partiality constant and we introduce P01, which was the pure pressure due to component 1. Okay. Now, there was a little modification in the formula, and I said that it is equals to P1 is directly proportional to Y total. And what is this Y total? It is the mole fraction of the same component in the gaseous phase, because when we are dissolving something in something, then of course vapors form in case of volatile substance. And yeah, more specifically, this formula is applicable to volatile component only. Yeah. So as we put this say two volatile component together, so both of these will form vapor above the solution. So the pressure of that component is directly proportional to the mole fraction in that vapor phase. Okay. So this Y total is of YI is the mole fraction of that component in the vapor phase. Then we remove the proportionality constant and introduce P total. What is this P total? It is the total pressure that is above the solution. Now, if we use this, say, our Dalton's law of partial pressure, then we can say that P1 plus P2. That is P total. So P total is equal to P1 plus P2. Okay. So P01 x1 plus P02 x2 is equals to P total. We can write this. Then we have said that we can write, since it's a binary solution, we can write x2 as 1 minus x1. Then we have taken common and we have introduced a new formula. So this was our Raoult's law. Again, we said that Raoult's law is Henry's law is nothing but a special case of Raoult's law, because Raoult's law is a general form. And what does this general form say? That for every volatile component added, its say partial pressure is directly proportional to the mole fraction. So we stated the general Raoult's law. So this was all our laws governing all types of solution that we need to study for our syllabus. Then we move to colligative property. We defined that we have a property which only depend upon the number of solid particles that we have and not on the nature of solid particles. And we named it as colligative property. So there are 4 specific type of colligative property that were elevation in boiling point, depression in freezing point, relative lowering of vapor pressure, and osmotic pressure. The first one was, and one more thing, the component that we're adding as solid particles are non-volatile in nature. Then and then only all these coming on formulas will be applied. The first one was elevation in boiling point. So what we have seen that upon the addition of this non-volatile component, the tendency of the solution to go into vapor phase decreases. Why is it so? Because it will decrease the kind of, you can say, it will decrease the tendency by forming or occupying some of the sites on the surface of that liquid. And since it is non-volatile in nature, it will be difficult for the solvent particles to escape. Now in that case, the tendency decreases, and we have said that whenever the vapor pressure of the liquid phase is equal to the atmospheric vapor pressure, then only boiling will take place. Now since the tendency to escape has reduced, its vapor pressure has also reduced, because tendency means to escape, and to escape has to apply pressure. So since tendency is reduced, the pressure that is applied by the solution is also reduced, and we will have to boil at a greater temperature for the molecules to escape and to go into gas phase. For that reason, we have a elevation in boiling point. We have to boil up to a greater temperature, and we have introduced a formula which was del TB is equals to kBm, where del TB was the change, or you can say the elevation in temperature, kB was the ebullioscopic constant, and m was equals to the molality. Again, we have a depression in freezing point. So similarly, when the vapor pressure of the liquid is equals to the vapor pressure of the solid, means and since we know that vapor pressure of solid is less, so when the vapor pressure of liquid decreases to the vapor pressure of solid, we get the freezing point. Now since the escaping tendency has reduced, so therefore it can easily freeze down. So there is a you can say a depression in freezing point. So it freezes at a much you can say a greater temperature than the freezing point. Due to this reason, we see a depression in freezing point. The formula is simple and is in analogy with the previous one, which is equals to del TF is equals to KFM, where KF is the cryoscopic constant and M is the molality, and del TF is the depression in freezing point. Now one more distinction between del TF and del TB. The del TB is final minus initial, where del TF is initial minus final. So this should be kept in mind. Then we move to this relative lowering of vapor pressure. So it was derived directly from our Raoult's law, and it was said that the relative lowering, that is relative lowering means lowering by pressure of the pure one, that is delta P1 by P01, will be equals to the mole fraction of the component 2. So it can be written as N2 by N1 plus N2. So we have taken a case where N2 was greater than, N1 was much more greater than N1, and we have written that N2 plus N1 is equals to N1. Therefore, N2 by N1 will be our final relative lowering of vapor pressure. Then we have removed this N2 by W2 by M2 and N1 by W1 by M1. So we get our formula W2 into M1 by M1 into W2. Okay, so this was our relative lowering in vapor pressure. Again, we move to this osmotic pressure, and we said that what is osmosis? Osmosis is basically the movement of solvent particle from lower concentration to higher concentration, so that the concentration in lower can be increased by decreasing the number of solvent particles and hence attaining the equilibrium. Now, what is osmotic pressure? So it is the pressure that we apply on the solution so that there is no net movement of solvent particle from lower concentration to higher concentration. And this pi was equals to CRT, where C was the concentration and the concentration term that was taken was molarity, and it is equals to number of moles of solid particles by total volume. So pi is equals to N2 by V into RT. Now what we have done, we have applied a pressure that was greater than this osmotic pressure, and we said that this pressure would not only stop the flow of solid particles from lower concentration to higher concentration, but it will also do the opposite flow. That means now the particles will flow from higher concentration to lower concentration, means the solid particles will flow from higher concentration to lower concentration. And how the solid particles were stopped from moving from here to there? By introducing a semi-permeable membrane whose size or pore size was that much, which will only allow the small solid particle to flow through and not the larger or hindered solid particles. And the reverse process was called a reverse osmosis. Now this same process was used so that we can do the purification of water. How? So how the purification was done? So we take fresh water in one compartment and saline water in one compartment. Now the natural tendency would be that the fresh water will move toward the solution, but we have applied a pressure at the solution side that is greater than the say osmotic pressure. Now the solvent particles start moving from saline water to the fresh water, and in that way we increase the volume of that fresh water and we get our fresh water, right? Now we have different kind of solution. The first one is isotonic. So the isotonic solution is R1, in which the two solutions are the same osmotic pressure, meaning that if we take a volume of both of them and keep in two compartments and separate it by a semi-permeable membrane, then there will be no net flow of this solvent particle from one compartment to another or vice versa, right? So this was the thing. Then we have the case of hypertonic and hypotonic. So for explaining hypertonic or hypertonic, we have taken the case of blood cell. So blood cell have a concentration of 0.9%. So if we place it in a solution that is having a concentration greater than 0.9%, then the water will flow from the cell towards outside, and this will result in shrinking of this cell. What will it will result? It will result in shrinking of cell, and it is termed as it is termed as edema. And the opposite case, if we take the solution, outside solution, smaller than our inner solution, then the water will flow from outside to inside, so that the equilibrium can be attained. And in this case, we see swelling of our tissues also. Okay, so these were the two. The one in which the water flows inside, we call it as hypertonic, and in which the concentration is higher outside and the water flow outside, we call it as hypotonic. Then we have some natural phenomena. The first one was the pickle one. So if you put raw mangoes in brine solution, so due to higher concentration of salt, all of the water flows from raw mango towards the solution, and we see shrinkage of this raw mangoes. Again, this is seen in the case of pickle. Then we have seen that the movement of water from soil towards upper part is also partially due to, you can say, some of this is due to the capillary movement, and many more phenomena are involved, but it is partially due to osmosis. Then again the blood cell, which I have told you earlier. So this was the case of osmosis. So till this class, I have covered whole of the part, and I have just given you a revision also, so that you can summarize all this in a quick glimpse. So with this, I would now tomorrow see three types of section we will see. So we will see three kind of questions. We will see CBSE, we will see JEE, MM and NEET. So one by one we will cover previous year, so that we can get a good clutch of all this concept. So this solution is much more scoring. So you must keep a hold of all this formula so that you can score in your appropriate exams. So thank you for today's time. So tomorrow we will start from CBSE part. Okay, thank you.